Hi, my name is Seonyuk Kim in EECS, and I'm going to cover the chapter 5.2 Bootstrap. What is Bootstrap? From the textbook, it says the bootstrap can be used to quantify the uncertainty associated with a given estimator or statistical learning method. Let me give you an example. Here we have two companies, X and Y, and the rate of return for investment. As we can see through the data, company has high variance and Y has low variance. I'm going to invest my money with a fraction of alpha, like this. So it will be expressed as weighted sum, like alpha x plus 1 minus alpha y. I want to prefer a low risk, which means minimize the variance. But how can we find the alpha that minimizes the variance with given data? Let's take this problem as in mathematical way. Here we have the problem. We will going to prove that given alpha minimizes the variance of the weighted sum. First, we take the target of and split it to variance of alpha x plus variance of 1 minus alpha y plus 2 covariance of alpha x and 1 minus alpha y. With the characteristics of variance, we can take the constant out from the variance and replace it with given condition, this. And we can rewrite the given covariance with expectations like this. After take the constant to outside, we can replace this part as sigma xy like this. Now we have these two statements and we will going to mix together. The target variance can be rewrite as follows. And if we reorder the statement with respect to alpha, you can see the quadratic functions like this. If there are second order quadratic formation, we know that minus b divided by 2a is the value of x that minimizes the y. Here's the same way. So this is going to be the a, and this going to be the b. And constant 2 will be erased. So to minimize the variance, alpha have to be the given statement, like this. That is the end of proof. To minimize the variance of weighted sum of variable x and y, we only need the variance of x, variance of y, and covariance of xy. We can find the best alpha that minimizes the variance. However, do we know real variance and covariance of x and y? I don't think so. We can calculate the variance of n covariance only with the given data set, and we will call this variance x hat, sigma y squared hat, and sigma xy hat. If we have another data set of x and y, the alpha value will be changed because since variance and covariance of the other x and y changes. So this is what we want to know. How much it will be changed. Reversely, how much it will not be changed. How much can we trust the calculated of the sigma x hat, sigma y hat, and sigma xy hat, and the calculated alpha with given dataset. This is what the Bootstrap does. Let's get back to our original problem. We have the data, and we can calculate the variance and covariance, and the objective value alpha. It says alpha is equal to 0.1274. So we need to invest more money to company Y to minimize the risk. It was natural because the data of company X has high variance and the company Y has low variance. We aim to invest our money to make it the low risk. That means low variance. So we need to invest more money to company Y. That's why the alpha is equal to 0.21274. However, can we trust this result? Not yet. Now we will do the bootstrap. Let's do the bootstrap. For bootstrap, we will make a kind of artificial dataset, like fake dataset from original dataset. Since we cannot generate the true dataset, I mean, the data from the true world, real world, we just make an artificial dataset from the given dataset. This might cause really big error, but it will explain it later. Anyway, we resample the dataset with allowing the duplicates. So some of the data can be appear many times. Like, for example, sample 3 has multiple, the first data appears multiple times like this. But it doesn't matter. Now we have multiple dataset. We can calculate the alpha with the generated dataset. From first resample dataset, the alpha is 0.0505. It's really low. The second one is 0.3868. And we do this many times, like 10,000 times. With this lot of alpha, we calculate the average, standard deviation, and 95% confidence interval. And the result is like this. So among these alphas, the average of alpha was 0.2030. Standard deviation was 0.4374, which is quite big, large value. And the 95% CI was minus 0.3624 to 1.1429. The calculated alpha hat, which was from the original dataset, is still in 95% CI, but the confidence CI, but the confidence interval and the standard deviation is too large. That means if the real new data is coming, the alpha might be changed a lot, and the calculated alpha might not be work for the unseen data. Then, last question. Can we trust the calculated value? No. These are the process of the bootstrap, and it enables us to do this kind of data-driven decision making. All right, then is there any limitation of Bootstrap? I already said there is a huge error in this method. Here we have simple example of estimating average. Let's think the real world gives us the value 1 to 5 in same probability. Then the real average will be 3, obviously. And somehow, we make the dataset, we get the dataset that have only the value 1, 5, 1. It could be happen in real life, and the estimated average is also 1. The model or the analysis cannot find the real average. Therefore, we calculate the average from our given dataset. To check if we can trust the estimated average 1, we use the Bootstrap and resample the dataset. But the original dataset has only the value 1, so the resample dataset is also always have 1. The calculated average from resampled dataset is also 1, and it does not have any changes, even if we resample multiple times. In result, the Bootstrap says, according to your dataset, the average is 1, and even if we resample the dataset like 10,000 times, the calculated average is not changes, so we can trust the value. But is this the right analysis? Of course not. Then why is it happen? That is because the dataset does not represent the real world well. The bootstrap is based on the trust that the given dataset represents the real world well. But if the size of the dataset is too small or too sensitive with outliers like median or max value, the dataset might not represent the real world. In some cases, even though the dataset represents the real world well, the resampled dataset could not represent the real world. For example, historical data and spatial data. Since we allow the duplication between the data while resampling, the statistical feature could be changed by resampling. This is because those kind of data has the relationship between each data. Then, how can I fix this problem? The simple way is to collect many data. As you collect many data, your dataset will represent real world well. But for this data, we cannot use the Bootstrap, or we need to find some new resampling method that does not break the characteristics of the data. Now we have the last topic. How do we use Bootstrap in machine learning? There are many ways, but I want to explain the analysis of coefficient. Let's think we have this linear model with 3 predictors. We resample our dataset and fit beta 1, 2, and 3 for each resampled dataset. After we fit all betas, we can calculate the variance, standard deviation, and confidence interval for each coefficient. If some coefficients 95% CI contains 0, that predictor might not affect Y, which means will be meaningless. There are no relationship between the predictor and the Y. And if some coefficient's standard deviation is too large, that we cannot trust the fitted value beta. It doesn't mean that we cannot use the predictor. So if the beta 2 is the case, it doesn't mean that we cannot use the x2 as a predictor. We still can use the x2, but we cannot use the beta 2, the fitted the value. Bootstrap can be statistical reason for parameter tuning. Then, how is it different with the t-test we use for check if the predictor is null hypothesis? Bootstrap relatively needs small number of data and relatively more robust for outliers. But if the data set is too strange or cannot reliable, this kind of problem will be happen. Anyway, compare with the t-test. It's more robust for outliers. However, it requires lots of computations. So if we try to resample like 10,000 times, we need to make a 10,000 sample data set and fit the betas 10,000 10,000 times. For this reason, we can just use Bootstrap with t-test for parameter selections, both of them. All right, so this is what I prepared for the Bootstrap. I hope you understand better and thank you for listening. 여기 이거 지금 이거 또 저거 안 먹혔으면은 오늘 하지 말라는 것 같아, 이거는. 근데 이거가 계속 뜨긴 하니까 이거가 되지 않을까 싶은 느낌? 그래도